Hey Dr. Lane. So for today, we're proving Young's modulus is equal to the spring constant divided by D. And we know the force of the spring is equal to the spring constant times the stretch. Stretch is just the difference in length after hanging something from the spring. And if you solve for the spring constant, that's the force of the spring over delta L. And we know that when springs are linked, they will stretch twice as much when hanging the same object as just from the first string. And parallel strings works the opposite way. They would stretch half as much. It's got twice the force against the mass of the object being hanging down with double the force of the spring. So, makes sense. And let's imagine that this is a wire, and we're going to imagine that the atoms are connected by springs. And we want to find the number of parallel springs and the number of linked springs in this wire. So D, we would have to solve for that, but it's just the distance between the atoms. And we would know the number of parallel would be all the ones on the first layer. The number of parallel springs is the area divided by D squared. And the number of linked springs is the length divided by D. That'll find how many linked springs there are. And we know Young's modulus, the definition of it, stress over strain. Stress is force of the spring over area, and strain is change in length over L, or this form if you like. So we want to find the interatomic spring constant. And to find that, we got to do the number of parallel strings divided by the number of linked springs times the spring constant. And then we just switch these out here with what we solved with our cross-sectional area analysis and multiply that by Ks. These cancel out a D, and you get A Ks over DL. We just move the D from the top to the bottom. And then we solve for Ks, and over here it's equal to force of the spring over delta L, right here, times solve for Ks again, that is DL over A. So Ks is equal to Fs over A, force of the spring over the area, divided by delta L over L, times D. D would be left over. And we know, if you notice, this here is Young's modulus. That's stress over strain times the distance, which equals Young's modulus times D. And now we want to get it in this form here. You just divide both sides by D. Boom, boom. And there. It's proved. So we know that if you know Young's modulus for a metal, you can calculate the stiffness of the interatomic bond with this formula here by just rewriting it in a different form. You just would need to find the distance. So, yeah, pretty cool stuff.